Ohio everyone! Since I got a bunch of anime to watch, I'ma skip the intro and jump right into the content. Just like the title implies, we're gonna code a decision tree. Most people have seen a decision tree at least once in their lives, but just in case you haven't, here are two examples. They're just tools to help you classify something based on certain factors. The one on the left is the most basic type of decision tree. It tells you something is part of a group or not. You would use these for simple yes or no decisions. The one on the right, however, gives you different classifications based on the route you take. For all intents and purposes, you can use these for yes and no classifications, but that's like using a flamethrower to light a candle. Cool but unnecessary. I've only learned how to code the basic type, so I'm only going to show you how to code the basic type. Obviously. The first problem to tackle in making any decision tree is deciding the root node, the feature you're going to base the classification off of, and the split factor, the threshold that decides how you split the feature. Both can be decided using one of the following, the GINI Impurity or Entropy and Information Gain. I'm not going to give the proof for any of these because I'm not a nerd like that. The GINI Impurity measures how impure a dataset is. For example, the first dataset is completely pure because it only contains zeros. The second is less pure because now it contains two different numbers. There's a joke about racism to be made here, but I'm not trying to get cancelled on my first video. The formula for the GINI impurity is 1 minus the sum of the probability of choosing I from the dataset squared, where I is each unique value in the dataset. For the example dataset 1, 0, 0, 0, we have one element in I equals 1 and 3 in I equals 0. From then on, the calculation is straightforward. Next is the entropy and information gain. The entropy of a dataset is simply the extent to which randomness can occur. In the first set, regardless of how you ordered the data, you still get 0, 0, 0, 0. On the other hand, in the second dataset, you can get a multitude of combinations. I'm not going to list them all out. Get that out of here. Anyway, entropy is given by the sum of the negative of the probability of choosing I from a dataset multiplied by the log 2 of the same probability. It is much easier to comprehend by looking at the formula, and from then on, the calculation is straightforward. The information gain is the amount of information you gain by predicting outcomes using certain values from a given dataset. Let me clarify. We want to maximize the amount of information we get per level on the decision tree as it is simply more efficient. For example, if we try to classify the dataset 1100 based on the feature set 0000, we still don't know what attributes classify something as 1 or 0. It yields a low information gain. On the other hand, if we try to classify the data 1100 based on the feature set 0011, we know that if something has the feature 1, it can be classified as 0, and if it has the feature 0, it can be classified as 1. The formula for the information gain is the entropy of the result or classification set minus the sum of the weighted average of the entropy of the result set corresponding to each I. Let me clarify that last part. In the example below, the result set corresponding to I equals 1 is 1, 0. The one in the first position in the dataset corresponds to the one in the first position in the result set, while the one in the third position of the dataset corresponds to the 0 in the third position of the result set. Similarly, the result set corresponding to I equals 0 is 0, 0. From then on, the calculation is straightforward. Now that we have the basics, I'll discuss the reason why we need to code a decision tree in the first place. Mr.Mackey, the school counselor at South Park Elementary, was told that a lot of students applied to their school this year, and that he was in charge of letting them in or turning them away. Okay? This year, Mr. Mackey didn't want to deal with any nerds in his school, but he's having trouble identifying whether a student is a nerd or not. He knows there's some correlation between watching anime, liking math, and being a nerd. Unfortunately, he doesn't know what that correlation is. Okay? So he told us to use decision trees specifically to find said correlation. Okay? He also told me that he's gonna break my kneecaps if I don't. I personally don't want my kneecaps broken. Okay? Okay. Now, Mr. Mackey was kind enough to provide me with this data that he collected scientifically, apparently. His dataset is coincidentally very simple and we can form a decision tree without any code. But since I know that Mr. Mackey is always on the lookout for an excuse to break my kneecaps, we'll use this as a test case to see if our code works. Now, from this data we can easily make this decision tree. If you're confused as to why this is the case, watch the video through once and come back to this point. Now let's get to the actual coding part. We'll first make a decision tree using GINI Impurity to determine the root node feature as well as the splitting feature, and after we'll adapt the code to make use of entropy and information gain. First, we need to properly format our data to make it usable. Since we want to be able to predict outcomes or print out a decision tree by calling a function, it would be wise to represent our data in one list, just like how it's displayed in data 1. The name list is only added to help visualize the decision tree. It isn't necessary in actually predicting values. I've also imported NumPy, since we will need to use functions in the NumPy library. Next, we need to create a GINI function. We don't want to have to write out the calculation every single time we want to calculate the impurity, now do we? This function calculates the total GINI impurity of a result set, denoted by res in the function, with respect to a feature set, denoted by featless in the function, and returns not only the impurity, but also the best split factor for that feature. First, we need to get a list containing the unique split factor, GINC, within the feature set using the numpy.unique or np.unique function. Then we set a counting variable, gtot, for the total impurity and two holding variables, gi and splitfac, which hold the impurity and factor value of the split factor with the least impurity. Then for each value I in GINC, we set three counting variables which hold the total instances of I in the feature set, the amount of corresponding ones in the result set, and the amount of corresponding zeros in the result set. After setting these variables, we check each element j in the feature set and check whether it is I or not. If it is, it checks whether the corresponding value in the result set is 1 or 0, and it increments the appropriate variable. You might be wondering why that line of code is highlighted. Well,
that's a surprise tool that can help us later.
Anyway, after the code finishes going through and checking, the GINI impurity for that I is calculated using the previously shown formula, and if that impurity is less than the previous impurity, then it sets the impurity of I as the new lowest impurity within the feature set, and sets the split factor as I. Lastly, the total impurity is incremented by the weighted average of said impurity, and after these steps repeat for each I, the total impurity for that feature set, as well as the best split factor for that feature set, is returned as a list. Now we need to create a function that trains/models our decision tree, denoted as decTreeTrain. We first declare four holding variables which will hold the best split feature, the corresponding split factor, and the name of the factor. That last one is not necessary when it comes to using the decision tree, but it will help us visualize it. Then for each element in our decision list up to the second last element, in other words all the features as the last element is our result set, we calculate the GINI impurity, and if it's less than the previous one, then the corresponding values are formed. Once we finish calculating all the GINI values, we then store the lowest GINI value in an external information list, known as inf. It is easier to just declare and use an external list as we must call the function on itself later on. Now that we know what the splitting feature for this root node is, we need to eliminate it from our data list, as well as all the values in each feature and result set corresponding to the splitting factor. This is because that factor in that feature classifies the data as per the corresponding values in the result set. It doesn't matter what values they have for the other features. If we go back to Mr.Mackey's situation and the decision tree we should get, if you like anime, you're not a nerd, regardless of whether you like math or not. We also do this for the name list, but again, this is only to help in visualizing the decision tree. We then call the decision tree training function on the shortened data list if the length of the data list is larger than 1. In other words, if there are any features left. Once all features have been eliminated, the information list is returned. However, this list is quite unsightly and hard to use as is. So we need to make another function that transforms it into a more useful list, denoted as decTreeTransform. We first declare our decision tree list, and then the following operations for each element or feature in our information list are performed. We declare another list, AVL, and then go through each position on the result set, the first element of the ith element of the information list. If the value in the corresponding position of the feature set, the second element of the ith element of the information list, is equal to the split factor, the third element of the ith element of the information list, we append the corresponding value in the result set to the list AVL. We then declare two holding values and one counting value. Here the first value represents the classification when the condition of the feature is met. The second value represents the classification when the condition is not met. Then, for each unique value in AVL, we count how many of that value exists in AVL using numpy.count0. And if that number is larger than the current count value, then the first holding value is set to that unique value, and the count value is updated. The second value is only considered when we're on the last feature because we are assuming that the data remains quite impure until it is split over all the features. If we're not on the last feature, the second value is simply considered none. Otherwise, it's just whatever the first value isn't. And because we're only dealing with 1s and 0s, the second value is given by 1 minus the first value, which gives 1 or 0. Once all the features have been transformed, the transformed decision tree is returned. Now we have quite a usable decision tree, however it is quite inconvenient to use. So now we can make a simple visualization of the decision tree by making the function decTreeNice. We first loop through each element in the transformed decision tree list, and print out the name of the feature as well as the split factor. This is indented by 8 times I spaces. Then, if the second value is none, the first value and the name of the next feature is printed, and again indented by 8 times I. I chose 8 because there are 8 characters, including spaces, before the second value. If the second value isn't none, which occurs at the last feature, the first and second values are printed. After each iteration, an empty line is printed to make the decision tree more legible. Now, if you look at the original decision tree and what we got through our code, the classifications are the same. If you like anime, you're not a nerd. If you don't like it but also don't like math, you're still not a nerd. Otherwise, you are a nerd. Now what we need to do is code a predictor function, decTreePredict. If we give it a set of attributes, it should classify that set based on our decision tree. We loop through each element in our transformed decision tree. If the value of the attribute set at that position is equal to the split factor, then that means the attribute has been classified and we return the first value. Otherwise, we move on to the next feature and repeat. Once we reach the last feature and if the attribute does not match the split factor, we classify it as the second value. The last thing we need to do before we can actually use the decision tree is make an accuracy function, decTreeAcc, to tell us how accurate our model is with respect to the original dataset. We first set a counting variable to count how many attribute sets have been correctly identified. Then for each position value in a feature set or result set, which one you pick doesn't matter because they are of the same size, we create an empty list. Then we loop through each feature set and add the value of that feature set at that position to the created empty list. Once all the features have been looped through, we call the decTreePredict function with the resultant list serving as the attribute set. Then we check if the predicted value and the actual value are the same. If so, our counting variable is incremented. The loop then moves on to the next position. A new empty list is created and the process is repeated. At the end of the loop, the percentage of correct values is returned. Now let's say we want to use information gain and entropy instead of GINI Impurity. We first need to code entropy and information gain functions, which can be coded like so, using a similar process to how we coded GINI Impurity. The only difference in the code from then on is that the initial information gain in the decTreeTrain function must be -1 instead of the 1 used in GINI Impurity. From then on, the code is the exact same. You might still be wondering about the highlighted lines earlier. If we edit the conditions of these lines, then the condition for classification is no longer being equal to a threshold, but now equal to or less than, and equal to or more than a threshold. If you had multiple unique values in a feature, it would be wiser to use this kind of condition for more accuracy. And with that, the coding section is over. If you could fully comprehend the concept of decision trees as well as how to code them, there are a couple of ways to make them more complete in a sense. Earlier in the video, I said that we've assumed that the data remains relatively impure until it's split by the last feature. What if this is not the case? What if the data can be classified using only a few of the given features? How would you change the code, or what new code would you add to integrate these considerations? Earlier, I also mentioned that there are different classification conditions you might want to consider. But how would you know which is the best option? This one is simple enough to code. You can create 3 different training, transforming, and predicting functions. However, that's quite inefficient. How can we code it in such a way that it is less taxing to check which type of condition yields the highest accuracy? If you have any feedback, regardless of what it is, please let me know down in the comments. And that's about it. Adios, pelo elotes.